Hello, my dear students. Good morning to everyone. In previous session, we were discussing some important rules for filling up of electrons into various atomic orbitals. The rules are Aufbau principle, Pauli's exclusion principle, and rule of maximum multiplicity. Okay. So, in previous class, I just defined Aufbau principle. Aufbau principle gives us energy order of various atomic orbitals to write electronic configuration of the elements. According to this principle, it states that this principle says that electrons first enter into orbitals of lower energy, then electrons enter into orbitals of higher energy. And this principle also gives us energy order of various orbitals and energy order of various orbitals that we have written, like 1s less than 2s less than 2p, 3s, 3p, 4s, 3d. It continues after 3d according to one diagram. Okay, I have drawn one diagram. According to that diagram, we have written energy order of the various atomic orbitals. And you try to remember energy order of the various atomic orbitals. This is most important. If you remember energy order of the orbitals from 1s to 3d, you can write electronic configuration of elements from hydrogen to zinc. Okay, here writing electronic configuration is must. Okay, everyone should know how to write the electronic configuration. In previous class, we have written electronic configuration of the some elements by using energy order, and in this class, I am going to teach you how to write electronic configuration of the elements from scandium to zinc. Scandium to zinc, we will write the electronic configuration. Okay, writing electronic configuration of the elements from hydrogen to calcium is somewhat easier, but writing electronic configuration from scandium to zinc somewhat difficult, that I am going to teach you. In addition to this electronic configuration, I am going to teach you Pauli's exclusion principle and Hund's rule of maximum multiplicity. These rules also I will cover in this class. Clear? First of all, let me explain how to write electronic configuration from scandium to zinc. Okay, calcium. Calcium is the 20th element. Calcium after scandium will come. Calcium after which element will come? Scandium. Okay, format. In the format, you have to write electronic configuration. Suppose if you want to write electronic configuration, you need element name, atomic number, energy order. Energy order you remember 1s to 3d. 1s, 2s, 2p, 3s, 3p, 4s, 3d. Clear? Now I am going to write scandium electronic configuration. The atomic number of scandium is 21. 21. It contains 21 electrons. Now let us write configuration. 1s2, 2s2, 2p6, 3s2, 3p6. 3p after, remember that. 3p after which orbital will come? 4s will come. Okay, 3s, 3p, 3p after 4s will come. 4s2, 4s after 3d will come. Here energy order somewhat different. 1s after 2s, 2s after 2p, 2p after 3s, 3p after 4s, not 3d. After filling 4s, electrons goes to 3d. Okay, without filling 4s, electrons never go to 3d. Why? Because the energy of 4s is less than 3d. Okay, so in between 3p and 3d, 4s will come. 3s, 3p, 4s, 3d, like that. So here the total number of electrons arranged in various atomic orbitals, that must be equal to the atomic number. Okay, here 1s 2 electrons, 2 plus 2 4, 4 plus 6 10, 10 plus 2 12, 12 plus 6 18, 18 plus 2 20, 20 plus 1 21. So here the total number of electrons arranged in various atomic orbitals, that is equal to atomic number. Okay, clear? After writing electronic configuration, you make sure that the number of electrons arranged in various atomic orbitals is equal to atomic number or not. Okay, now let us write shell configuration. How do you write shell configuration? Shell configuration means number of electrons present in K, L, M, N shells. Okay, let us write. Now, in scandium configuration, if you look at scandium configuration, K shell contain 1s belongs to K. K shell contain 2 electron. L, 2s2p belongs to L. Total how many electrons present in L? 2 plus 6, 8. And 3s3p belongs to M. 3d also belongs to M. 3s3p 3d belongs to M. Remember that. 3s3p 2 plus 6, 8. 8 3d also belongs to M. Okay. 8 plus 1, 9. 4s. Remember that. Okay. 4s comes in between 3p and 3d. 4s belongs to N. 4s contains how many electrons? 2. So the shell configuration is 2, 8, 9, 2. K contains 2 electrons, L contains 8 electrons, M contains 9 electrons, N contains 2 electrons. Clear? Now coming to titanium. Titanium atomic number 22, that means 22 electrons it contains. Configuration 1s2, 2s2, 2p6, 3s2, 3p6, 3p after 4s2, 3d2. In d orbital up to 10 electrons you can arrange. The maximum capacity of d to hold the electrons is 10. So d orbital can take maximum 10 electrons. This is titanium configuration. Now shell configuration, 1s belongs to K, 2 electrons. 2s 2p belongs to L, 8 electrons. 3s 3p 3d belongs to M. Total how many? 10. Okay. Now 4s belongs to N. 4s contains 2 electrons. 2, 8, 10, 2. Okay, clear? Now coming to vanadium. Vanadium atomic number 23. It contains 23 electrons. Now configuration 1s2, 2s2, 2p6, 3s2, 3p after 4s2, 3d3. So shell configuration 2, 8, 11, 2. Okay, clear? Now chromium configuration, it is entirely different. The configuration of chromium is entirely different when compared to other elements. Here I kept a star mark besides chromium. Why? Because it is exceptional case, anomalous configuration of the chromium. Anomalous means what? The configuration is somewhat different when compared to all other elements. Generally, up to 30 elements, the configuration of chromium and copper are different. The reason I will say little later. So first let me write configuration of chromium. Okay. So the reason I will tell you later. Why the configuration of chromium and copper are different. The atomic number of chromium is 24. Configuration 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. Remember that. Not 4s2, 4s1, 3d5. Here in chromium, half filled d orbital is possible. Half filled means what? D orbital with 5 electrons. If d orbital with 10 electrons, that is called as full filled d orbital. Generally, half filled d orbital, full filled d orbital gives extra stability to the atom. Okay, if any atom with half filled d orbital or full filled d orbital, that atom is said to be more stable when compared to other element. In chromium, half filled d orbital is possible by shifting one electron from 4s to 3d. In chromium, one electron jumps from 4s orbital to 3d orbital, so that chromium gets half filled d orbital. So extra stability of chromium which is achieved by half filled d orbital, and this half filled d orbital is possible when one electron from 4s is shifted to 3d orbital. So how one electron is shifted from 4s to 3d, that I will say later. Clear? You remember in chromium half filled d orbital is possible. See, at last you can see half filled d orbital. This is half filled d orbital. Okay, clear? So instead of 4s to 3d5, the configuration of chromium will be 4s1 3d5. Okay, at last. Okay, instead of 4s to 3d4. Okay, instead of 4s to 3d4, what is the correct configuration? 4s1 3d5. 3d5 means half filled configuration. Okay, now coming to manganese. Manganese atomic number 25, configuration 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d5. Manganese onwards, chromium, manganese onwards, the electronic configuration follows same. Okay, so shell configuration 1s2, 2s 2p L, 3s 3p 3d 13, 2 plus 6 8, 8 plus 5 13, 4s contains 2 electrons. So this is manganese configuration. Clear? So the remaining elements configuration I will tell you